Good afternoon. Welcome to final session for the day. Just as a reminder, as you are leaving this afternoon's talk, there are 2 pods at the back of the room that you can use to swipe your card and provide speaker evaluation and talk evaluation. We'd appreciate it if you would do that. So at that point in time, I will turn it over to Nathan Keltner and Josh Thomas for SoCsploitation.
So first, thanks everybody for showing up late in the day for the last BlackHat talk. We appreciate that this is the talk you chose. So agenda, we're going to go over just what a SOC is in general. Then I'm going to actually dive into why Harvard chips are cool, why we don't actually see very many of them, and just the mental shifts that you have to do between the x86 von Neumann-esque architecture that we're used to and actually exploiting Harvard. We'll go into just the general hardware reversing process that we use, and from there we'll transition into the actual Teridian chips that we're going to talk about. We'll do a full live exploitation, and then we'll also talk about glitching and other more advanced hardware techniques. So
I'm Nathan Keltner, and Josh Thomas. We both work for Accuvant, and we do work like this, projects like this for our day jobs.
But we found a vendor we had not worked with yet to do this.
Yeah.
So, what is a SOC? SOC is a system on a chip. It's everything you need. It's basically a computer. Everything you need to run whatever you want to do, except for voltage, which you have to get from the wall or some other place, and software. But I mean, it's a computer. Full microcontroller, memory. Typically, a lot of the peripherals are built in. You see them a lot in any embedded devices. You also see them in cell phones. Pretty much everything other than your laptop typically runs a SOC. Cars are another exception, or another thing that you see them in. One of the reasons that they've got so much great market share right now is because they're incredibly cheap and they're incredibly low power. So pretty much every new product that we see that we're attacking on a day job is powered by a SOC. And we have Harvard. So when we're dealing with x86 or old ARM or things like that, we're typically looking at von Neumann architectures. When we look at von Neumann and how it works, we're used to having a code section and a data section. We're used to being able, the CPU to be able to grab between them. You may have tricks like NX and stuff, but that is used to only be software. Now it's software and hardware, but it's an add-on. When you look at how Harvard works, right?
Yeah, conceptually, right, x86, everything is sort of one big address space. And then we divide it up at the OS layer, right? And so, now we're doing some things at the hardware layer, but so where your data is, or where your code is, or your stack is, any of those types of things, those are all potentially mixed and matched, and it's not anything different at the hardware layer. So when an instruction says, operate on this address, then there's the one place that it goes and it does whatever that instruction does. Whereas Harvard, right?
Yeah. So everything's one big chunk. When you start looking at Harvard, Harvard is actually cut into 2, right? So I have a code section that has buses that go to the code section, and I have a completely disjoint, not hardware connected, separate piece of memory that is data, and I've got separate buffers and buses that go there. Never the 2 shall meet as far as the technical spec and design. That is Harvard. So when we do that, like I said, we don't really have NX, but we kind of have NX anyway because we don't have code and data in the same place. One of the cool things that we start seeing is this dual bus allows prefetching to not get in the way of other things, and the system can be optimized like crazy. So you start seeing almost every instruction that runs on the device is single cycle. So we've got it may be technically slow, but it actually runs fairly fast at low power.
Yeah, one of the things that the Teridian chip that we're going to talk about later in more detail, one of their selling points or whatever on it is that it's got about an 8 or 16x speed increase over other cores that are similar for the same clock per clock cycle, because they can do basically everything in one clock cycle. So there's very few instructions that take more than one.
Yeah. So what we started seeing when we start poking at Harvard a little more, we start seeing the first headache we see is that, like, because the buses are different, because it's physically separated, we can have program and data actually have different bit widths. It starts to be a pain, but not really for us. It's just interesting. Crazy registers. You typically have custom compilers and custom tools. You have banking headaches, which Nathan will get into in a little bit. And then things like pointers and stacks are just awkward or gone or work way different. If you're interested in Harvard as a overview and just kind of getting a little more into the whole technology, if we don't cover enough for you today, Travis Goodspeed did an excellent talk at NoSuchCon. Really, you should go look at that.
He basically covered like 10 different embedded chips and then tips and tricks on how to do exploitation on all of them. Unfortunately, none of that really applies to this one, and so like the stuff we're talking about here, there's not a lot of overlap, but it's the same space. So if you're interested in this, it's great work.
So our typical hardware reversing, just what we do, how we do it, how I attack a problem, how Nathan attacks a problem. We tend to work with smart meters. We tend to work with things like that. We're talking about a lot of voltage running through your desk at home. First warning that we hear at every presentation that is talking about smart meters is you have high voltage you don't want to touch. Touching high voltage sucks. We've all done it. Every one of us has at least run 110 through us, right? And it hurts. Don't do that. So be careful. Logic analyzers, they're great. You can start latching onto chips, which we'll see in a second. Start figuring out what's going on. Almost every type of Harvard chip or any sort of embedded chip that you're going to look at will typically have a custom debugging board. You can also start playing with the GoodFET, which we've done quite a bit for this project, but sadly we're not releasing anything yet. Because it never quite worked the way we wanted. Bus Pirate, I mean, typically you want to be able to figure out what's going on the wire, then you want to figure out how to actually debug and start playing with things.
Right, it's all just about figuring out what are those interfaces there, right? So just figuring out what talks to what, how can I interface with that, how can I monitor how the pieces are interfacing with each other, and then in what ways can I influence execution state.
Yeah. And the last kind of pro tip that we've got before we really get into the meat is if you're working on high voltage or typically almost any embedded system you see, if you are powering that device, like we're failing here, but if you're powering and you're running ground on the same plane that you're running your device, like if we're running 110, that your laptop doesn't like that, and you end up doing things like frying your USB ports.
If PCBs were designed correctly, that would never be a problem. But when you get into like debugging interfaces and stuff like that, like there's a couple of them out there that are known for letting you electrocute yourself or frying your laptop.
Yeah. So this is kind of just we got a couple pictures that I'll just walk through real quick. This is a typical setup when we're starting to hit hardware and start digging into it. What you can see in the foreground there is we've got very tiny micro grippers actually gripping onto the sock as it's soldered onto the board. So it's running, it's got 110 volts through it. And then you can see past the beer. No, it does.
No, the chip doesn't though.
That's true, the chip doesn't, the board does. But you can see like halfway back, we've actually got the vendor supplied debug port. So I'm actually being able to control debug, but as I'm doing that at a software layer, those little micro grippers are actually letting us do a full logic analysis on what's going on the wires, so we're able to track more things than the vendors let us get to, and start digging a little deeper. And then again, kind of the same picture, just from a different angle, where basically every time we attack something like this, we're really trying to just figure out what's going on. My thing is really what's going on at boot. Where are things getting loaded from? What can we do? Our end goal typically is I need to dump this firmware so I can then throw it in IDA and I'm back in a comfortable spot. So Teridian. These are the chips we're going to talk about today. There's a ton of Teridian chips on the market. They're one of the biggest vendors for smart meters. So you see them everywhere in the smart meter space. We've started seeing them a lot in pin pads, any type of distribution automation or home automation. They were originally Teridian Semiconductor, and then they were bought by Maxim, and now they've got a huge market share. But because they already had a good name, Maxim kept them. For the most part, we only see these on the metrology side of a smart meter. There's not really any space that they're touching on the other side. Do you agree?
So it's doing the metrology side always, right? So it's always doing the side that's actually like measuring power. And so if you have a smart meter on your house, there's a good chance that one of these chips is actually in it, performing that function. And then how it talks to everything else, right? That gets different. There's standard interfaces into this chip. The serial is the most common one, and then that can talk to whatever they want it to talk to. And so it could either talk to another board that is an entire computer in its own right, and it's doing whatever it's doing, and then it's just ferreting commands back and forth. Or it could just be doing like straight pass through, and like in the Teridian chip itself could be speaking something like ANSI C1222 is the one for network communications, and then you've got like actual packets terminating inside the Teridian chip itself.
So when they're not hooked up, you have to have physical access to be able to pop this. As soon as they're hooked up to any sort of radio interface, now you actually have a valid remote attack vector, which is logical, and it's not really jumping anywhere from where we're comfortable with. A couple more pro tips. If you ever get into the space, if you ever start poking in a SoC in general, Teridian is wonderful about this. They have dev boards where they're trying to sell big vendors, millions of these chips to start building hardware with. So they make a demo board that has great open source code. It's open source, kind of open source hardware. They're relatively cheap, so they're great because the whole chip is broken out completely already. I've got nice code so you can start figuring out what the chip is doing, at least as far as the vendor. So then if you have a specific target you're looking at, you at least know what reference they started with. And you can look at the board, which here's a demo board right here. It's the one we're playing with today. But you can start looking at the board and looking at all the specs that come with it and pretty quickly figure out, this is how I physically put the chip into debug mode, this is how I enable JTAG if it's been blown. It's a much easier than just starting blind. One of the things we always want to do is we want to dump firmware, right? And a lot of times that's very difficult on production gear. It's not impossible, but one of the things that we found that is actually significantly easier than fighting with production gear, I buy the demo board, I take my production gear, I run chip-quick around the whole production gear SoC, I pull that off, and then I resolder it on the demo board, and now I've got everything broken out. JTAG is miraculously in hardware enabled again, and we can just use the standard tools to dump firmware. You can't really do that live in the field as an attack vector, but if you want just to get the device once, it's really the easiest way to go. Second thing, when you start wanting to look at these type of devices and how they work, you really want to figure out what the PCB is doing around the SoC just as much as you want the SoC. One of the tricks that we have started to do more and more is I take a board, like a production board, and I desolder everything. And just like, that's all the detritus crap that was on the board. I'm sure it's important for it to run, but I don't care at this point. I take that, I throw it away. Then I throw the bare PCB in a flatbed scanner. I scan both sides, and then I just throw it into the GAN per Photoshop, and I start tracing all of the traces. And now I have a complete PCB layout, just like I would if I was the electrical engineer actually building the PCB to begin with. Now I can start enabling and disabling filters in the GIMP, and I can fully understand how that hardware is working.
And of course, there's different types of PCBs, right? So you've got ones that have multiple types of layers. As a general rule, the ones that we've seen, those middle layers are primarily just either like ground planes or power planes, that kind of thing. So there's not a lot of complexity on those, and you can usually kind of figure out what they're doing. Yeah. So we've not had anything really complex that's bothered us with yet.
Yeah. And I mean, meters, the demo boards are $250. Meter boards, or meters in general, tend to be really cheap because they're just mass produced like crazy. So once we've done the full deep analysis of actually how the board works, then we can start working on a live PCB. We can start playing with it when it's got power through it, when it doesn't have power through it. typically what we find is, and this is just general, not really Teridian specific, but typically what we're looking for when we want to dump firmware is just shift the chip into a different mode. So it's ungrounding a pin, it's grounding a pin, it's crossing a pin with power. These are how the hardware actually works. So this is what we're going for when we're really trying to understand. You want to talk about code tracing?
Oh, sure, yeah. So some of the chips support what's called code tracing over the debug interface, and some don't. So like this demo board that we bought here, we had a long, hard argument or discussion, I guess, with Teridian, where we were just trying to get some of this stuff because it was on back order for extreme periods of time. And so we ended up finally just switching and ordering this one at the last minute quickly because they had it. And then later I discovered that, it doesn't have code tracing. And code tracing is basically, it's what it sounds like, right? It exports the full state of all the registers at every single cycle. So the debug application that they use will give you like full like the ability to go backwards and forwards through execution state. So as the program's running, it makes it so much easier to figure out what's going on. And if you're doing, trying to figure out exploitation, if you're just trying to figure out, maybe how it's like pulling in and it's decrypting a certain part of itself to like pull keys out or whatever you want to figure out, it's so much easier if you have code tracing. So unfortunately, we don't have that to demo because the one that we have doesn't have that, which makes various things harder. But it's only a slight difference in the debug, this expensive debug interface thing that we had to use. So it's worth it to just as a heads up that they don't all have it. So it's worth it to find it. All right, so I'm going to switch gears a little bit. I'm going to talk about this chip specifically, and we're going to use it to kind of walk through an example of how the Harvard architecture works on this one and how exploitation works, or how the pathways that we've figured out for it. So this is like the overall schematic of what is inside that SoC, right? So we're talking about that a SoC's got everything that would be needed for a given use case. So for this case, we're talking smart meters. So it's got stuff to like drive the LCD screen. It's got stuff to like say pin pads. It's got stuff to to drive the pin pad that's on there. This has got lots of inputs that are designed specifically for measuring measuring power usage in an accurate manner for smart meters, right? So every single SoC, like all the Teridian SoCs, all have a very similar structure, and then they've got like an 8051 core, and they've got memory, and they've got these things, and then they've got different peripherals that they stuffed in for the different use cases. So zoom in a little bit, and we're going to look at these two to start with. So what we're looking at here, that's the MPU microprocessor, and the CE is something specific for doing the power measurement calculations. So the MPU, the 8051 derivative, that's an Intel chip that's been around forever. That one's very, very ubiquitous. It's in lots of places in sort of everyday life. This version of it is one that has just been massively parallelized, or however you would say that. It's got the ability to do lots of things in just one instruction cycle, right, that we were talking about earlier. So that's the major difference on that. It's byte aligned, which means that you can kind of jump wherever you want, right? You can do things like ROP if you wanted to, if you were able to control the stack. So it's useful on those sides. The computation engine is something that we don't really care about from a security perspective, just knowing that it's there and it will occasionally step on you. So the problem with the CE is that it and the microprocessor share flash memory. And so basically there's timers firing off all the time saying who's allowed to have or who's allowed to be running. And so you'll be doing something in your code, for example, and then suddenly the CE will kick in and it'll like lock you out of flash memory in the middle of what you're doing. And so it's just something that you have to keep in mind, like when you're doing exploitation on this kind of stuff. There's all kinds of other things that are happening via interrupts or via timers that are going off that are outside of your control, and you don't necessarily know that those are happening. So the very first thing that you usually do is you go and you start shutting all that kind of stuff off as soon as like your shellcode hits. So yeah, the major things that we care about on this particular architecture, 8051 core, the memory, and then the ICE components, the ICE being like a JTAG analog, if you're familiar with that. Okay, so let's talk about memory, right? So we've got these four basic different types, and we really only care about three. So there's flash, external RAM, and then internal RAM. So memory map. So talking about where is flash and what's that look like. This is where code and occasionally static data is stored. So if you're writing this kind of code, it would be like you want to be putting things like keys and stuff like that in here for some other reasons we'll talk about later. But static data is also stored there because it's a large amount of space. So like I think one of the biggest things that's stored there in like the demo software, for example, is just all of the like the text, like the ASCII that's used for like the help thing on like one interface. So so it's got code and data, but it's never modified data, and the data usually has to be copied somewhere else before you can do anything with it. Flash memory itself can't normally be modified. So true Harvard would mean that this would be read-only like all the time. And that so you would load it, you'd load code with like a JTAG or whatever, and then you send the production device out, and then it never gets modified ever. Now reality, right, is that nobody can do that, right? Nobody can ship code on a device and then never update that code again. So what that means in the real world is that that nowadays Harvard architectures require the ability to somehow modify flash memory. So you got to jump through like 10 different hoops to make that occur. But the general statement is that you can't modify it. So that makes it hard, right? If that's the only place that code can ever be loaded from, that's the only place that instructions are ever run from, and you want to change the thing, like you want to drop shellcode on it, and you want to do whatever you want to do, that is obviously that's the major barrier on Harvard architecture. Unique to this, it's we're talking very small spaces, so it only addresses 64 KB at a time, and then the half of that gets swapped out. This thing called banking. So the bank switches. So like the top half is always there. So like that first 32K is always there in that address space, and then the next 32K gets rotated out by a certain value in like a bank select bit register. And so whatever's set in there tells you what data is accessible over there, and that brings you all kinds of headaches when it comes time for exploitation. In software, it's not really a big deal because you just load up the settings for the compiler. It knows what chip that is, and it just automatically handles all that for you. So you write normal C code, and you don't really have to care about most of this stuff because it'll automatically load in the libraries and do all the bank switching for you. However, if you jump in via some external method where you've been able to do some of the stuff we're talking about here, or talk about later, where you're able to actually get code execution, then suddenly you have to deal with all that stuff, and so it's a big headache. Flash is really weird. So I don't know if you know a lot about Flash or like how it works, but like when you get to the point where you actually can start modifying it. So let's say that you bypass, you do those 10 hoops so that now you can make modifications. Well, the way Flash works is that it's not like an on-off switch like what you normally think about. The way that it works is that you will mass erase a whole section of it at once, and what that does is it turns all the bits on, right? So basically it resets everything to FF. And then when you code it, you turn off select bits to give it a certain value. So what that means is that if you want to make a modification, you end up that you have to reset it to FF first before you can put an arbitrary piece of data in it. Or you have to find a place of code memory that's already full of FFs. But it's very different than just like normal RAM or like what we think about on hard drives and stuff, where you just can just push something and just say go do that. If you don't know what you're doing and you don't know what the state of it is beforehand, then random writes will just fail because it can't create that state, right? Because it's all a series of just which bits are turned on and which ones are off. And yeah, you can only erase pages of Flash, not bytes. So if you want to make a small modification to the code, right, what do you have to do? Well, okay, crap, I've got to pull this whole page of code from over here into RAM, and I got to make the modifications that I want. I got to do a mass erase on this page from over here, and then I got to copy it back. And that's kind of painful to do from shellcode. All right, so yeah, so what do you have to do? Right, what I just walked through. The other things you got to do, like that I mentioned earlier, you got to make sure you turn off interrupts and turn off CE, things like that, because it'll step on you right in the middle of it. The way that this particular Harvard implementation works, like I mentioned, that normally you can't ever modify the code page, you can never modify Flash. The way that it works is that there's this movex instruction, where normally what that means, it's saying copy data to or from X data. So X data being a very particular section of memory. Or where all the data is stored, like all your variables and all that kind of stuff, not code. And you flip a certain bit, and suddenly that same instruction now makes a modification to the Flash memory. But again, that's difficult because it's the same instruction. So if you happen to have that bit on longer than it should be, and like some other piece of code runs, then suddenly like all of your Flash just got corrupted, right? Because every single instruction is, like every single function is dealing with movex commands, because that's where it's storing arguments and pulling data out, things like that. And so like if you don't get this thing switched off fast enough, then suddenly something else will run, and it thinks that it's storing code like on, or fetching and storing code or storing data over in RAM, but instead it's actually corrupting your firmware. Right, so computation engine will step all over you. And then there's one other thing that's on here. It's not really a security feature. It's more of just to make sure that that certain sections of memory don't get overwritten. It has a way for you to set certain bits that say turn off the first X pages of flash from being able to be mass overwritten. So like that would typically be where you would store like boot code, for example. Something like that, like a sort of failsafe, or it's the code that loads everything else. And so you put that there, and then you never want it to be overwritten. But it's just a bit, so there's not a security feature of that. You can just go in and change it if you need to. Right, so we can unset bits. In certain specific situations, you can be happy with not having to do that mass erase trick.
You can craft, but it's got to be
you can craft.
that in a binary 1 and 0 format, you can still flip from a 1 to a 0 and then recraft your data, but you have to, that is a huge headache.
Right. There's been some stuff on other architectures where this matters a lot more, like some of the stuff that Travis has talked about on, I don't remember which architecture it was now, but the particular way that like the compilers on that architecture worked is that they would store certain types of stuff that you could modify up higher than stuff down below that you cared about. So like what you would end up being able to do is you could unset certain bits, and then you could drop a pointer to being a lower value, and then you could jump out of that particular area that you were in. So like the upper area would be this protected area that you can't get into, for example, and then you unset some bits, and then suddenly now you're down in like the equivalent of userland. Right? We can't do that here because we kind of have the opposite problem. All the code that's already there is down below, and then the only places that we would ever modify are up above. So you can't go higher, but you could theoretically go lower. All right, so next section, right? We're going to talk about IRAM. They're down there at the bottom. So IRAM is really small, right? What is it? 256 bytes, I think. Yeah, and so that's where so special function registers. Yeah, we don't really need to know what those are, other than just that's where you store certain types of bits on like the state or the configuration of the processor. And then basically what's in here is your stack for the most part. And so it's really small. And so let's see. Yeah, so depending on compiler and settings, the stack is usually there. But the problem is that it's so small that variables aren't. So that's another major difference, right, from the stacks that we're used to. Variables are never stored here. The compiler basically always sticks them over in Xdata, and then it hard links them. Or it'll just embed it directly into the code itself if it knows that it can do that. So that makes it really hard for exploitation, right? Like you think about any type of exploitation pathway that deals with the stack. None of those are really valid on this particular architecture, because like any sort of let's say like a memcopy bug, right? Let's see. Any kind of memcopy bug, you would not be able to modify the stack in this case because you're not actually on the stack, right? All your variables are someplace else. All right, so XRAM. So this is the one that we primarily are the most interested in and have the most interaction with. This is where variables go. Because that's where variables go, then that's what you end up being able to corrupt. All of the, whenever a mistake is made in code, that happens, and it's some sort of mistake that allows you to modify like the variables that it's dealing with, right? So like if it's a memcopy, right, that I talked about a second ago, and it allows you to overwrite something. Well, in this case, you'd be able to overwrite things after that in Xdata. But again, we don't have stuff that's there. We don't have registers there. We don't have, you don't have the ability to overwrite the return value, for example, because the return value is not there. It's in someplace else. All right, and then so we'll come back to that here in a second when we get to the actual exploitation stuff. But then this last section that's specific for this, we'll talk a little bit about the emulator, and that's what this JTAG-like thing is. It's a proprietary undocumented debugging interface, which basically means that you've got to buy the expensive one. But once you have that, then you're able to talk to it. We've looked at a little bit of trying to reverse this out and do some of it ourselves, and there's some possibility to do that. It's similar to the ChipCon debugging interface, which is also made by Intel. So it's similar to that, which there's some code for in the GoodFet base, but it's still pretty hard. So that's one of the things that we're continuing to work on. What we'd love to be able to do is release the ability to do at least certain types of debugging without requiring this device. So if we can get to that state, we're going to be releasing that code. But for now, this is what we have to use. So the way this works. So you think about JTAGs, right? And you know that like JTAGs have these fuses that are there, and you can blow a fuse, and then the JTAG interface is now turned off. In this case, it doesn't quite work the same way. It's not on whenever you first turn on the machine, or when you first apply power. For the first 30 or 60 instructions, the processor is in what's called pre-boot phase. And it's turned off during that time period, and then at the end of that pre-boot phase, which is either 30 or 60 cycles depending on, it may be depending on documentation version, and rather not chip. I think somebody made a mistake, but it doesn't matter. It's so small that it's imperceptible for us for the most part. And then it gets turned off. It's turned on by default every single time you apply power, right? Like it would be on by default every time it turns on power, unless you set a specific bit that says, hey, don't turn me on. The pin pad ones are a little bit different. They allow you to permanently set that bit that says keep this thing off, but this one doesn't. But so like pin pad 1 is more like a JTAG fuse. We've not actually looked at one of those, so I don't know how robust that is. If you can use similar types of attacks that have been used on JTAG fuses to try to get back into it. But they say the documentation anyway says that it's permanent. Smart meter socks chose to not do that. So there are certain security ramifications to that. All right, and then last case here, we'll talk about the interfaces into this guy. So you've got serial UARTs, or a serial UART that's just kind of standard like you would think, and then it also has hardware that's designed to speak to an optical interface on the outside. That's the looking into the eye of the meter, like Cutaways talked last year, right? That's where they match on the pinouts. And right, these interfaces are where all your problems are, right? Because this is where you actually get to interface with code. So remote exploitation occurs over these types of interfaces. Right, so Cutaways talked about doing doing exploitation or finding bugs at least over that optical port, doing it on that side. There's another serial port that's on the other side of this that then talks to the world, right, somehow. And whoever that's doing that, whatever that's handling, that's where your problems are going to be. Right, yeah, plugin Cutaways talk. Any bugs found on that side will likely be found on the inside, because of the way the standards work. They're using either the same or a very similar ANSI standard on both ports. So whatever you're able to find on the outside via like Cutaways tool, for example, if you just happen to to play with that, something very similar would likely be also triggerable over the network side. So the thing with Cutaways talk, right? It's really, really cool stuff, but we're talking about plugging onto a meter on the outside. If you find a bug that allows you to do that, and you have a way to be able to get on the network, which depending on the architecture, there may be dozens of ways to do that, and you can send packets to this thing, then you'd be able to trigger the similar types of bugs. All right, so let's talk about sort of bypasses for some of the things we've talked about. Okay, so the secure bit, right? This is the thing that says, let's prevent the ability to use the debugging interface, right? So this says, I'm not going to let you externally read flash memory. I'm not going to let you, light up the debugging interface. The way to unset that. So it's not, like, again, that is also not a permanent flag, right? The way to unset that kind of stuff is to hit it with a mass erase so that you wipe out the code that is setting that in the first place. So in the first 30 or 60 cycles, what's normally happening is that there's a instruction that runs that sets this bit and says turn off the debugging interface, pre-boot phase ends, and then the debugging interface does not come up. So how do you get back into that device, right? So they didn't want to just have that be a bricked scenario. So the common way that these guys will do it, and MSP430 does it the same way, and others, it'll let you go ahead and without being able to light up the full debugging interface, you can perform a mass erase. So what does that do, right? It resets all the flash to FF, but there's an important consideration here, right? Did they also think to clear all the other locations? Because that's not the only location where something sensitive is stored. Right, so this is the screen that pops up on the debugging interface when it's in secure mode, when that bit has been set. There on the left is what it looks like whenever that's been set, and it's basically saying no, you don't get access to any of that stuff. But then after you do a mass erase, well, now the code is gone, but all the data is still there, right? So like this is an example here that we just used where we had some code that loaded BlackHat into memory, and then we wiped that code. And then we light up the debugging interface, and then wow, I can still see all that stuff. Now, that may or may not matter depending on the particular use case. So, I mean, right, this is like being able to see RAM without being able to see the code. So you don't necessarily have any context to know what these things are, outside of knowing what the device does, right? So if the device does things like, let's say it's a smart meter, and let's say that it's doing encryption as part of an ANSI standard. Well, you know certain things about how that's going to work. You know the things about like what type of encryption it uses. You know what sizes its key sizes are, things like that. And coincidentally, the way that that's implemented in code will most commonly always require you to copy that key out of code memory into RAM to then perform operations on it. So if you have a live meter, you can try to authenticate with it, or try to begin encryption operations with it. It'll load its key into RAM somewhere, and then you do a mass erase, and then take a look, and then, oh look, check that out. There's the key right there. Right? So that's a hardware problem. Like, that's something that can be fixed. And it's not just a Teridian problem either. MS-3430 does the exact same thing. There's several other chips in this embedded world that do the same thing. So, right, XRAM is accessible once flash has been mass erased. After you do that hard reset, it comes up. Power is never lost to that, so even though portions of it would normally go away, like when power shut off, as long as power is maintained, then the data is all still there. And so where did you store those keys, right? And then, unfortunately, even if you stored them in code, half the time they get copied over to data at some point anyway. All right, so let's talk about code execution. All right, this is what one of the main points of the talk was. So code is in separate locations, right? There is no concept of being able to execute code from data. Like, the instruction pointer can never point over there. There are different buses. It makes no sense. So there's no way to do that. The only way you're going to be able to get this is that you've got to be able to find a way to divert execution flow, and then once you've got that, then you've got to be able to piece together the components to jump through those 10 hoops, like I said earlier, to actually make modifications to code. And there's some things that happen in real life that make that a little bit easier. Because the stack's over in iData, in the internal RAM, and variables are over in external data, over here, normal vulnerabilities will not work, right? It's just incredibly hard to leverage those. And then, unfortunately, even after you gain execution pointer control, you still don't have control of the stack on this architecture. Because whatever mechanism you're going to use to gain execution flow is not coming through the stack, right? So you don't have control of that. Or you may have the ability to see it or like modify it, but you can't do that in any sort of like contextual fashion. You don't necessarily know what it is. So you can go and you can clobber it, right? But that's not gonna give you any help. So let's talk about a standard overflow, right? So standard memcopy type thing. Once you've got, whatever that type of bug would be, you've got the ability to make modifications to X data, right? But there's nothing important there. So how do we do it? And it's not necessarily just an 8051 thing that this does it, but it's Teridian specific. So there are other, I think Travis's talk that we plugged earlier, he speaks of another 8051 implementation where this is doable because the stack is in a location that is bigger in comparison, and so the compilers for that one don't do this sort of trick where it sticks the stack over here and sticks the data over here. So in those cases, standard buffer overflows would work just fine, but they won't in ours, unfortunately. And then because there's another side of this too, so what we end up looking for, right, what you're ultimately doing is you're trying to find pointers, right? You're trying to find some sort of pointers stored over an external data that you can then modify and then trigger some code execution path that will then fire those off and get them for you. But there's a few reasons why those are really hard to find, right? So normally, right, they're on the stack. They're, as part of normal execution flow, and you pop one on and you go run a function and then you return back. But even outside of that, the compilers know that, it knows a lot about the state of the program, right? And so what it'll do is that half the time it just embeds like a hard-coded value into the code anyway. So there's not a lot of pointers that are accessible anywhere because they're all permanently static over in read-only memory. But so let's talk about like the ways that you might be able to do this, and the ways that we'll demo this here in a minute. So the ANSI Smart Meter Standard uses concept of tables, right? So if you saw Cutaways talk, you know all about this stuff, or if you've seen one of the other ones. But it's when you're reading memory out of data or reading memory off of a meter. Let's say you're doing something similar, like you want to know how much power usage has been used over this period. What you do is via the standard, you ask it the right way to say, hey, give me the contents of table 10, whatever. And then if you've got access rights to do that, it'll give it to you. Well, so the spec, of course, tells you what's valid. It tells you what tables are real, what tables are not. And so, of course, you have common programming errors where you code only to what the spec says. So it's common to see, or vulnerabilities do exist or have existed that that did not account for being able to like ask for table values or things like that that would never happen in the normal part of anything, right? And so when that happens, you could see something like this, right? So let's say that you've got some table value, and then you're taking a table index that's coming in from like a request. It's saying I want to see table 10, for example. And if that's implemented in arrays, then you'll see something along these lines where it feeds a value in. Now, what this looks like, and if you've not seen this type of vulnerability before, what this is, it's complete arbitrary control of external data. So what this would give you a write anywhere in external data. Because what that is that you can keep increasing the table index and it'll overflow itself. And then so the array will just happily, like the array may only be, it could be like say 10 bytes over here, and you just keep grabbing indexes all the way off the end, and so you can keep reading all the way around, and then your integer will go ahead and overflow, and then it comes back over here and reads from in front of it, and so you end up getting the ability to read or write to the whole thing depending on what the bug is. So okay, so we can write to arbitrary locations of XRAM, right? So we can do that. And of course having the same type of read runs. Well, what are we going to write, right? How are we going to do this? How are we going to find what we need to modify? How are we going to find a pointer over there somewhere that's going to divert execution flow for us? One of the things, we mentioned this demo board, right? One of the reasons that we chose this to talk about it is because it's this architecture that we wanted to speak about, but it's an open or sort of publicly available board that just anybody can buy, and then we can publicly talk about it. This comes with sample code, right, that is given to you as a potential developer. You want to build smart meter apps. And so the demo board comes with common features that you would want to do in the real world. One of those is using this thing called software timer interrupts. It grants the ability for functions to be called after a certain number of cycles have occurred. Why it's there is because hardware timer interrupts are relatively expensive because you don't have a lot of them. So like on this one, I think you've got maybe like 4 hardware timer interrupts. And so what those are just, you call it with like basically say, I want you to invoke this function after this many cycles have run, or I want you to do this particular callback whenever this interrupt fires. And but you may need more than 4, right? So what their library does is it implements software timers on top of those. So it basically takes one hardware timer and multiplexes it out to like 8 or 16. But ultimately, right, what that means is that there are arrays somewhere that are sitting in memory that contain function pointers, and then there's another array next to it that contains how many cycles to run in between when it should fire, right? Okay, so let's say that, so at this point we know we've identified some pointers, we'd like to modify those pointers. How can we do that, right? So, well, we can't modify flash directly, we already know that. We can't execute data anywhere else. This implementation only executes functions in that first 64K, which makes things more difficult, especially if you're trying to do something like ROP-like with taking advantage of the sort of the 1-byte alignment stuff. And then additionally, you've got all the banking issues. But again, the real life scenarios kind of come to the rescue. Even though architecturally that could be really hard, those are the same problems that the code has to solve for itself. So code blocks exist that do most of those heavy lifting. In the real world, right, you're going to have things like bootloading and reflashing code. So somewhere you're going to have code already that does all those things for you. It disables interrupts, it turns off the CE, it flips the bit, and then it copies a particular value from over here into flash memory. And then it reverses itself and steps back out. So that code's going to be there somewhere already. Again, for this, we just copied, there was another library from Teridian just that gives an example of how to do it. And so we would just use that as a great public example. We stuff that into our code, and then that's what we end up leveraging in the exploit here in a minute. Okay, so STM, right? How does that work? Here's what the functions look like. You can see the STM start function is just taking a function pointer and it's taking how many counts that you want, and then it stuffs that onto that array fn_PTRS. And then later there's another one that says, hey, if one of these is inspired, then let's go ahead and call it. So this is just a grep through the source tree for this particular sample thing, and this is just pointing out there's all these different locations that are using this functionality, right? It's used by the serial ports and the command line interface stuff. It's used by EEPROM. It's used by the LCD screen on the front. It's used everywhere. So that means that when you walk onto a device after you've got exploitation, working, that means that those arrays are already going to be populated. There's already going to be arrays there that are doing this for you. So you can just modify them, and your things will run. All of the locations where the stuff is going to be stored are static for a given piece of compile. So once you locate where that array is stored, it's going to be the same for like every single version, or for every iteration of that version, right? So that means all the meters are going to be the same. That array is going to be stored at the same place on all of them. You just have to compute the index that to feed into your your bug that we talked about earlier, and then it will allow you to make modifications to that location. Now the stack is still logically split here because of how the compiler sets it up. How the compiler does like hard links over here, and then there's the real stack over here. Now what we're able to do is we're able to fire off function pointers, so we're able to gain code execution, but we still don't have control of like other stuff. So like I can say, hey, okay, I'm going to override a pointer and I want it to run to this function over here, but that function maybe is expecting something on the stack, right? That happens occasionally. And so it'll look up something on the stack and then point somewhere else. Well, that's really hard. So you've got to figure out where the locations for variable storage are, or you have to find which functions are actually using variable storage in static locations in external RAM, which happens most of the time because of the compiler. And then you modify those. So like when you think about the way that, the way normal function control happens on like most of our platforms, you stuff a few arguments or a few pointers to arguments on the stack, and then you jump to that location, right? And then, or you're stuffing them into registries or registers. In this case, all that stuff is statically. They're from static values in external data. So when you jump into a function, that function has hard-coded values just saying like grab from address 1234 and I'm going to use that for this, and grab from 1238 for this. So once you find those, you make modifications to those locations as well, and then the last step is you overwrite the function pointer and the STM stuff, and then finally your code executes. Now the problem, and why I say pray here, is because of course this is we're doing this in a really sort of strange way. We've got race conditions because we're modifying what the variables are, and then you wait, and then you're modifying saying go ahead and execute this function. So it's not all together, right? Like it would be in any sort of like sane world where you would say run this function with these variables. Here you're saying let's modify these variables first, and then okay, let's run whatever's there, and let's hope that whatever's there hasn't changed, because that does happen sometimes just in normal flow of the execution. You have no contextual information about any of that other stuff, which of course is more painful and during that process where you're trying to figure out how to make this work. But in state, once you finally get there, you've got resident code execution on ours, and then it's there forever, right? It's not going to go away until the thing's been reflashed. So we'll kind of do a quick demo of what this looks like. All right, so this is looking at this is the debug interface application, just a Windows application that does all this. I've already got this loaded up and it's running. So what you're going to see here, so I've got a script over here I'm going to run that's going to interface with the serial port where this bug exists and this bug didn't exist in their demo board because the demo board itself doesn't actually implement any of those standards. It doesn't actually implement anything for talking to the outside world. It's just meant for showing off the chip. So we had to implement our own interface on that and then have the bug in that. So that's what we're doing. And again, and I guess the overall point of this talk is not necessarily about specific bugs in smart meters that are out there right now, but talking about once you find those bugs, because they're out there, once you find them, what do you do, right? And so that's why. So we've got our demo one over here. Code's already running. So you're looking at like here. This is address 6000 in program state. Currently, it's all FF because it's blank. We're going to see that get modified here in a second, and then execution flow is going to jump into it, and then that's basically our landing pad where the first stage of shellcode runs. That then starts making modifications to other parts of the OS to do what you want it to do. All right. Let's see here. That's right, so we're setting different variables for functions that we want to call. We're starting to upload shellcode, executing that flash write and saying actually make the copy the shellcode over from XRAM to there, fix up the STM array to make it happen, and make it not crash afterwards, and then finally redirect execution flow. And are we gonna work? There we go. And so, so in this case, we're talking about like a fake demo board here, so like, it's kind of hard to figure out like what's the best way to show off that bug. But here, this is what we've got. Like, we've modified this particular range. You can see because it's red now, it's been modified. It's not ever supposed to be able to be modified. And then we stuffed our own code in there, and then we jumped to it. And there we go. All right, so that's kind of the bulk of it where we went. I think we've got a couple minutes that we'll cover glitching real quick.
So if you remember way back, we talked about there's some bits that can be set that don't let like ICE be enabled anymore, so you can't actually do any live debugging on the board. Unless you magically hit it within that first like 30 to 60 cycles. Once you do, you can get away from that. But we kind of wanted to do something a little sexier, and it was one of the reasons we're not releasing the GoodFet code, because we went tangential down this path and the GoodFet just couldn't quite keep up with where we wanted to go. We will get there and release it hopefully at some point. So we've got that pre-boot that is like 60 cycles, and in that 60 cycles, somewhere that security bit gets set. We just need to keep that security bit from getting set. When you start looking at all of the Teridian documentation, which is just massively fabulous, like it covers everything in the world you would ever want to know as a developer. They give you the demo code to turn that up, and they tell you exactly where to put it. So, you know, they say the very first thing you should do is, this is what your code looks like. If you do this, security will be set, and you can't debug the thing after it gets out of pre-boot. It'll never actually go into ICE. So we compiled that in, threw it in, started looking at it. What this code actually translates to is long jump, set secure but, and then something else. So we're like, okay, we just need to stomp all the hell over that third clock cycle after boot. Like, you give power, boom, I need to kill that third clock cycle. That thing doesn't get set, and then I'm good. Like, the thing will boot, I can get in. So that's the goal, right? We want to hit cycle number 3, just glitch it, and we're fine. Constraints that we've got with that type of glitch, right? We're running at 10 megahertz. We have to hit cycle 3, and we've got to hit it hard on the dot. Because we don't want to hit 1, we don't want to hit 2 necessarily, right? Because if you want to still have it running and be live, you still want those jumps. You just don't want that third thing to hit.
Well, maybe, right? It doesn't always matter. Yeah. If your end state is that you're just trying to get this thing up so that you can pull the code off of it. And then once you've got that, that's great. You'd be able to make whatever modifications you want to it and then reflash it. Yeah. So you can be extremely exact with it, and everything will still run correctly. Or you could not be extremely exact with it, but you'd still get the debug interface. So as long as the thing doesn't like constantly go into a reboot loop, for example, and if you can get past that and long enough, you can keep it alive long enough to let the debug interface be up, then you'd be able to halt execution, and then at that point, you've got the debug interface. So. Which
is something he reminded me of, because I was focused on that like clock cycle 3 and was like killing myself, and then he was like, dude, you don't have to hit it. And I was like, it got a little easier. So at the end of the day, we probably can just stomp over every damn thing that's in those first 60 cycles, and we'll get through enough to dump code. So we've kind of got 2 approaches, right? If you want to go with the open sourcey kind of hardware type thing, you've got the GoodFet, which is not remotely fast enough to actually pull this off unless you're going to be sloppy and just step over everything. And it looks like we can do that, right? So this is what that approach would look like. It's just like a massive like table flip, I don't care. And then you've got the Dot and Crank approach that was released at Recon.
And if you're not familiar with the Dot and Crank yet, you should look into that stuff. Basically it's just an FPGA that's hooked up to tons and tons of buses. So like it'll let you interface with whatever you want to interface with, and then you write FPGA code to do all that. It's a really fast way to be able to monitor lots and lots of things all at once, or be able to do things like this where you're monitoring lots of things and then also changing stuff. You're providing stuff at a specific value or whatever, specific speed.
Yeah, so that approach would look like this. It would be like, I just want to hit that one instruction and be able to do it. We started down this path. We were about halfway through with the GoodFet stuff, and then we actually got Data and Crank hardware, and we got really excited, and we started like completely diverging, which is one of the other reasons we didn't finish with either. But when we got the hardware, we were talking to one of the other guys at Recon that was trying to do something completely different with the Teridian chips and accidentally pulled this off.
One of the sort of the kind of a funny aside, like how vulnerable this thing would be to glitching, and others as well, I'm sure. When you're stepping through the source code of like their demo stuff, like so I said earlier that we copied over the bootloader code from that they had released and used that. So you're stepping through the section that deals with like flash writes. And like every third line or something, it checks this value. And it's saying like, am I supposed to be doing this? Am I supposed to be doing this? Am I supposed to be doing this? And finally in one place you find a remark from the author that says, because of like normal electromagnetic interference, like in storms and whatever else, the execution pointer gets corrupted like all the time. So like just in normal usage of the thing, the instruction pointer will like jump someplace else and then it just goes all crazy. And it's okay because there's a hardware watchdog that is paying attention and it'll just reset it if it gets too out of whack. And that's not a big deal for that. But it points out like a funny aside where it's like they had to put all these checks in because they wanted to make sure that the execution pointer didn't ever just accidentally get corrupted by like a lightning bolt or whatever and then jump into the flash overwrite section and then corrupt like the whole world and then it'd be bricked forever. Right? So that'd be really bad. But if it's really that vulnerable, like this just happens in normal situations, then that means that obviously you'd be able to induce that state. You'd be able to divert execution flow when you want it to. So you could say, don't execute the secure bit. And because of the way the architecture is set up, if you don't execute the secure bit, then the thing lights up just like you want.
And with that, I think we're done. I think we've already mentioned Cutaway and Alice and Travis a ton. Also want to thank Dr. Springfield. He was actually really helpful with this, which is Braden. I'm Josh.
Yeah, Nathan. Thanks, guys.
Thanks.